Hello, everybody, and welcome to this afternoon and lunchtime session. My name is Liane Benning. I'm the president of the European Association of Geochemistry, and I'm standing in for Lori Riceberg, which is the president of the Geochemical Society, because she lost her voice. So I'll be her voice. Any mistake I make are due to me. Basically, it's together with Lori, we are very honored to present you with the 2016 Geochemical Fellows of the Geochemical Society and the European Association of Geochemistry. This award was created 20 years ago, and each year we recognize about 10 outstanding scientists who have made major contributions to geochemistry. Goldschmidt, Tribes, and the Science Innovation Award also receive the honorary title. What I would like to do now is I would like to call the names of the people, and then would like for them to come up, receive their award, and stand next to us for a photo at the end. You see all the distinguished names and photographs up there, and I hope the photographs will do correctness to the people who actually will come up to the stage. The first person which I would like to honor is, and I'm really sorry for everybody whose name I will not say quite correctly, is Yamane Asmeron from the University of New Mexico. Thank you very much. The second name is John Blundy from the University of Bristol, who received the EAG Science Innovation Award. Thank you, John. Stand around this way.
Thank you.
Thank you very much. The next person is Elizabeth Conwell from the College of William and Mary. Turn around, please. Thank you. The next person is Sun Ling Chung from the Academia Sinica and the National Taiwan University. Thank you very much. Please turn around. The other way. Yeah. Thank you very much. Then we have Chongqiang Liu from the Chinese Academy of Sciences. Thank you very much. Around. Thank you. The next person is Isabel Montañez from the University of California, Davis. Thank you. Thank you very much. Next person is Friedhelm von Blankenburg from the GFZ in Potsdam and the Free University in Berlin. My colleague. Thank you. And the last one who is present, but not the last one who gets the award, is Ed Young from the University of California, Los Angeles. Thanks, Ed. We also have several new fellows who could not be here in person, but I will still want to name them. It's Bernard Boudreau from the ENS in Lyon, Carol Frost from the University of Wyoming, Patrick Hatcher from Old Dominion University, who is the GS Tribes medalist, and Jochen Hofs from the University of Göttingen, and Jay Queda from the University of Arizona. And I'll now go on the other side for a group photo. Group photo. Thank you very much. And I would like to call now Yongfei Zheng to come up to give the Shon Su Sun Award.
Yeah, on behalf of the Sun Su Sun Foundation, I would like to introduce to you the awardee and Hui Hejiu, Hejiu Hui. And Yeah. The Sun Shu Sang Award is designed to recognize outstanding young scientists under the age of 40 who works in mainland China, Taiwan, and Hong Kong, Macau. And the award will be presented by Professor Yongfei Zheng from University of Science and Technology of China. Professor Yongfei Zheng is a stabilized expert and academician of the Chinese Academy of Sciences.
Okay, we'll try to get through this, though my voice is going. As most of you know, the Goldschmidt Conference is organized in alternate years by the Geochemical Society and by the European Association of Geochemistry. And it's become a tradition for the sponsoring society to invite the president of the sister society to give one of the plenary lectures. For that reason, it's a tremendous pleasure for me to invite Liane Benning, President of the European Association of Geochemistry, to give today's lecture. Liane did her PhD at ETH in Switzerland, and she then spent 3 years, first as a postdoc and then as a research associate at the Penn State University in the United States. And since returning to Europe, she's taught at the University of Leeds in England, where she's a professor in experimental biogeochemistry. Since 2014, she's also the head of the Interface Geochemistry section of the German Center for Geoscience in Potsdam, Germany, and is in addition a professor in interface chemistry at the Free University of Berlin. Liane's research uses a wide variety of techniques to try to elucidate, in a quantitative manner, the geochemical reaction mechanisms occurring both in inorganic and in biogenic systems. And today she's going to talk to us about the fascinating work she has been doing on trying to understand why Greenland is melting. So let's give a warm welcome to Liane.
Thank you very much, Laurie. Normally you have to stand at the podium, but I'm really bad at that. So I want to first do this. Do this. I will forget to say thank you to all the people who actually have done the work. All my colleagues, whether they were PhD students, postdocs, junior or senior colleagues in the UK, Germany, or other places. Without them, nothing would have worked, and they allowed me to do the fascinating science, which I think is really what drives my day. Normally, people think I will talk about something like this. Those who know my science will think I will talk about how and why nanoparticles form, how and why, if they crystallize, can we understand, for example, how this helps us understand, for example, how coccoliths form their shells, what this means for global biogeochemical cycles, how we take really tiny nanoparticles and follow them in situ in real time to make beautiful giant crystals, or how we take minerals, we dump some microbes on them, and figure out how we go from a rock to a stone. That's what I would normally talk about, but I'm not doing that. Today I'm talking about something which is very close to my heart. I went the first time after my master's, I went to Svalbard for the first time, to the Arctic. And I utterly, hopelessly fell in love with it, and I've been in love with it since. It's the most fascinating place, and I had no time and money for about 10 years between my master's and afterwards to go back. And I was lucky to go back in 2003 with a bunch of people who are here in the audience, and since then I've been going every year, except 2011, where for me, because I wasn't up there, it was the most miserable summer possible, because I was in continental Europe. Not that continental Europe is that bad, but up there it's much better. The reason why I want to talk to you about today, because even in this short period of time, I have seen changes. I have seen islands appear where there used to be glaciers. I've seen ice bridges collapse where there used to be big glaciers. I've seen retreat of glaciers to a degree which is, I thought, initially very strange, but it's actually unprecedented. So I will still talk about how small things affect big global cycles, but I will show you a little bit of what happens today at our poles with the biggest, the biggest effort, which I will talk about, will be about the northern part. The reason why this is important is because we have, since Industrial Revolution, we have changed dramatically our planet to our anthropogenic world. This is downloaded from yesterday. We have reached 406 ppm at Mauna Loa, and just 2 weeks ago, we had reached more than 400 ppm also at the Antarctic South Pole. If you look at where we were at the beginning of the Industrial Revolution, at about 275, in the last 50 years or last 70 years, we have dramatically increased our temperature, our CO2 emissions. Naturally, this also has gone into a temperature increase. This is a beautiful heat map where you have months here, years here. This is from Ed Hawkins, where he basically showed how the temperature has increased during our since industrial time. And in November 2015, we have for the first time globally surpassed the 1 degree above pre-industrial level of our temperature. This is not the first time that we have hot or cold environments on Earth. Throughout geologic history, and for those of you who know that I'm not a geologist, in the next 5 minutes, please excuse me if I say a lot of stuff which may not be totally correct, but in the big sense of things, we had snowball Earth. We had a variety of glaciations, we had hot houses, cold houses. Why these things formed or why they melted, there are a variety of reasons which people have debated over many, many papers. For example, if you have a snowball Earth, one of the ways you can melt the snow is by having a lot of volcanic eruptions, putting a lot of ash into the atmosphere, making that ash land on the ice, changing the albedo, starting to melt the ice. One of the other ways you can produce an ice house that has been recently suggested was the fact that, for example, for the cryogenian ice age, you had algae, the rise of algae in between, and they produce a lot of biological molecules which go in the atmosphere which act as ice nucleation particles. So that could have been, according to some, a reason for glaciation. But interesting, what happens that when you had these big ice house, hot house changes, you actually see not just the rise of oxygen or the change from algae to fungi and higher plants. And I'm thanking for Paul Hoffman's website, Snowball Earth, which is fantastic for these slides. I also promised Friedhelm that I will put a slide with isotopes on it, because he knows that I'm not a big isotope person, but here it is. But actually, our geologic records throughout the time, and now I've gone to 500 million years to about 800 million years, really beautifully record these variations in carbon isotopes, which together, especially at the end of the cryogenian snowball Earth, almost full snowball Earth, whichever part you believe, has actually changed and actually led to faunal diversity increasing both at the order and the class level. So you think, well, why is this important? Because obviously, this way. Obviously, during the Phanerozoic, and now we are from 500 million years onwards, we had big changes in CO2, and this is from Bob Berner's work, where we see that the CO2 levels have varied dramatically over the last 500 million years, with the big drawdown of CO2 coinciding with the development of plants, the angiosperms in their fungi and the gymnosperms in their fungi. Today, we are here. And over this 500 million years, we had the hot house and the cold house, so it's, again, nothing new. I'm now jumping from 500 million to the next period, which is the last million. But if you look at the temperature fluctuations here, and this is from the epic ice core in Antarctica, which covers 800 million years, you see variations which are really scary. This is 15 degrees, but this is 25 degrees temperature difference. Now, this is Antarctica, given to that. But if you look at this the same way, and now you look at 1,000 years before present, 800,000 years, this is now the CO2, PCO2, and the methane, and it has the same kind of oscillation. Hot, cold, goes up and down. However, this is what we have today, which is far beyond what we have. We have reached the 400 ppm in CO2, and this is one potential prediction for the future. And this is what is really scary, because what this also does, obviously, it melts glacier, because the easiest way to melt ice is to make it hot. I have here some predictions which have been made by Ruža Ivanović, my colleague in Leeds, and these are basically showing how in the last glacial maximum, at the end of the last, during the last deglaciation, the northern hemisphere ice sheet and the southern hemisphere ice sheet are slowly disappearing. And you see, this should start again, you see that a lot of the Laurentian ice shield here has basically melted away. The same thing with Antarctica, but to a much smaller extent. If you look at it in terms of contribution, what you see is that the biggest contribution is from the Laurentide ice sheet, from the North American part, with Antarctica, small things, Fennoscandinavia, Greenland, etc., having smaller contribution. The scary thing on this slide is this axis. It's 130 meters of sea level rise. And the fact that it happened relatively quickly. This has obviously been driven by a whole kind of solar forcings. You had the solar forcings which are here in the middle, and I'm sorry for this fuzzy slide a little bit. But basically, you have up to 130 meters of sea level rise. You have the temperature of plus 4 to 5 degrees, depending how you look at it. And you could have an ice loss of about 3,000 gigatons per year, which is a huge number. And this is from Laurent Gregoire and, I don't know, John Peltier, I think, from Laurent is also a colleague in Leeds. The problem is that you had during this deglaciation a lot of inputs of fresh water, because obviously in the moment you melt ice, you have a lot of fresh water. What else does the contribution of ice do? If you think about melting that and that, you put a huge amount of fresh water into the oceans. And obviously the salinity gradients change the global circulations, which is just one of the potential consequences of melting the ice. For what I will focus on today, it's primarily the fact that when you melt ice, which especially comes from a terrestrial environment, you put a lot of particulates into the ocean, and these particulates obviously act as nutrients for the plankton and change the bioproductivity. And what happens, this is a picture from the east of Greenland. I'm sorry, this just came out yesterday. I couldn't download it at the speed we have here. This is June 2012. These are beautiful chlorophyll eddies on the east of Greenland. And the reason why you have to remember 2012, because 4 years ago, 2012 was the highest melting rate in Greenland ever recorded. Why is this important? It's because if you look at how much ice you have in Antarctica and Greenland together, if we look at how much ice there is to melt today, we could only add about 67 meters of sea level to our planet, which I think many of the cities at our coasts would not necessarily be very happy about. The difference for today is the fact that we have an order of magnitude difference in terms of runoff. That means the amount of water which comes off Greenland is about an order of magnitude bigger than the one from Antarctica, while the amount of icebergs which deliver their load, both in terms of water and particulates, to further distance out from the continent is almost double for Antarctica to Greenland. But importantly is that fact that over the last 2 or 3 decades, we have seen a tremendous increase in melting on Greenland. Everybody who is in this audience knows that actually the Arctic is the fastest changing part of our planet, but we also have quite a good data set to actually back that up. One of them is what you see here is a time lapse from 1979 to 2009 of the annual days of melt in Greenland. And obviously the more red you see, it's supposed to start again, but it doesn't. The more red you see, the higher the melt. Important what it is that actually we thought in 2009 we are in trouble because we have up to more than 75 days of melting, and then 2012 came along. 2012 at the time was the first time I went to Greenland. I was down here. You had seen more than 100 days of melting in Greenland, and also what you have seen that the melting was not just in the coast like before, but it was also in the interior. And you reached potentially up to 10 to 20 days of melting over the whole of Greenland. That means what you do, you don't just lose the peripheral glacier, so to speak, but what you do is you lose a lot of the interior mass. And you can follow this, and this is GRACE data, where basically you look at the mass loss between 2004 and 2015. It's not just dramatic, but it's actually accelerating. And if you look at this picture from 2015, this is the amount of melting which you have just in Greenland. This is the same plot where you have on the average between 200 and 250 gigatons, which is billion tons of ice per year you're losing from Greenland. And it's accelerating, and basically the Greenland ice sheet, in comparison to the global average temperature, which was 1 degree, has way surpassed or actually reached its tipping point, which is about 2 degrees for Greenland alone compared to the pre-industrial. The fact that we actually can see this even in satellite images, this is a picture from 2015, which was another year which everything was more and more. You see surface melting. This is a MODIS picture, where you see the surface melting. This is the little gray area here. And in 2015, melting started even earlier than in 2012, 2 weeks earlier. And we thought, well, it can't get any worse, can it? And then 2016 arrived. This year, we haven't surpassed just every record we've ever measured in Greenland. We've surpassed every record every month of melting. Melting started already, if you look at the temperature difference, this is the temperature from 2016. It was May warmer in February, March, April, and May. And by a substantial amount, we had in April, in Kangerlussuaq, which is in the west coast, we had 17 degrees, while we in Leeds were freezing at at about 0 and to +5. And I don't know what other people had, but it was warm here and cold here. And we thought it can't get worse, and then June arrived. This is the month we are in now. This is the land surface temperature anomaly of Greenland in June, obviously only the first 2 weeks of June, because we are still in June, I think. But if you look at this scale, across the whole of Greenland, you had, in big parts, an anomaly which almost reaches 20 degrees. In the capital of Nuuk, which is down here, you had 24.7 or 0.9 degrees temperature in Greenland. Never, ever recorded before. And at the same time, at the same latitude in other places, we had 17, 16, and 15. So this is an unprecedented melting, which we need to think about what actually does it do to it. This is what it does. It's melting, obviously, easy. Physics is very simple. You take something cold, you put it in something hot, and it melts. But it produces these vast amounts of water. This is a picture from 2014, where we had one of the other catastrophic melting, where the river actually took out this bridge because they were so fast, so catastrophic, that they actually destroyed that bridge in one single outflow. The same happens when you put from icebergs, which are actually calving from terminating glaciers, you actually have particulates which are in this, which are getting delivered to the ice, to the water. So regardless whether you have rivers, which can have, this river, for example, has about 12 grams per liter of particulates. That's a lot. This is an iceberg, so basically when these eventually reach the ice, they drop their load, and actually that part leads to a change in the whole global chlorophyll production. If you look at the next slide, which is, I hope it works, yes. So basically, you look at the austral summer and the summer up here, so you see the difference. This is month, goes from 2002 to 2013. Every time you have summer, you increase the productivity, specifically in the northern oceans or the southern oceans, depending on which summer you are in. So there's a direct link of how this works. But we were still asking ourselves, what actually makes this productivity go up? What do we deliver to make primary productivity happy in the summer months of the austral or the northern territories? So the first thing you do, you look at the Arctic rivers, and most of it now we'll be talking about the Arctic. If you look at the Arctic rivers, and if you look at the bars which are not hashed, that is the discharge in kilometer cubed per year. If you add all the bars up, you probably get to about 2.2 to 2.5 cubic kilometers per year of water discharged just by the Arctic rivers. If you look at the hashed bars, that's the sediment load, and actually that is relatively small. That is about just a little bit over 100 teragrams of sediment per year. What do these rivers bring with them when they reach the Arctic Ocean? They bring carbon, in dissolved form quite a lot, that's the gray bars, but also particulate organic carbon. They bring nitrogen. Again, the ratio is different because in red now you have particulate nitrogen and you have dissolved organic nitrogen, where depending on the river is slightly different. This is all the rivers around the Arctic which have been analyzed so far. And then you add Greenland. So at the moment, if you look at the white bars, just the white bars together, they make up about 1,500 cubic kilometers per year. And if you look at the particulates, that's by far outsourcing anything which comes from the river. So all of a sudden, you're putting about 800 teragrams of sediment per year into the Arctic Ocean and into the Atlantic. And naturally, you're not surprised that it does this. It creates blooms whenever it can. It creates blooms at any possibility, whether you're taking it from a glacier, whether you're taking from an iceberg. And in 2006, a colleague of mine, Rob Raiswell, and I was asking me, so what do you think is in these particles? And I'm a person who likes to look at like to use microscopes to look at stuff. So we started looking at the particles in them to try to see what are actually the nutrients which feed the stuff in the ocean. And actually, we started looking at the iron chemistry, and I will only focus on the iron chemistry today, because we looked at the iron chemistry to see how bioavailable it is, whether it changes during the transport from a glacier, whether it is part of the continuation of working inside an iceberg. And many people since, and ourselves, we have actually seen that much of this is actually really good, yummy food. And when I say yummy food, I mean both the ice sheets and the icebergs, and at both poles, they have highly reactive nanoparticulate iron. For those of you who are mineralogists, this is called ferrihydrite. We also found schwertmanite, which is strange, but we found that because it's produced inside the icebergs, inside the glaciers, because of the dissolution of pyrite, but actually all of it is really, really yummy. But then we ask ourselves, how yummy can that be? And we tried to look at the difference between what happens, for example, off Greenland, and compare it with, for example, Libyan dust which gets delivered to there. And we're coming back to the dust in a second. The important thing is that dust also gets processed in the atmosphere. You start with unreactive dust, and you process, and you also make ferrihydrite. But we were still wanting to see the difference because, for example, for the Southern Ocean, we had calculated that we have delivering by glaciers and by icebergs is about 1 plus or minus 1 teragram per year of iron, while through dust to the Southern Ocean, you actually deliver 10 teragrams per year. So we were wondering, okay, let's look at the bioavailability. And then we used my favorite toys. I like synchrotrons, and I like high-resolution microscopes, and the acronyms don't matter, but these are basically analysis of iron-2, iron-3 ratios in some of the particles which we looked at in many of these different samples, both glaciers, both icebergs, both northern and southern hemisphere. And what we see is actually there's a huge proportion of iron-2, which makes it so much more bioavailable. And we're trying to figure out why that is, and the important thing is that when we looked also at the dust, this is the Libyan dust sample, the ratio of iron-2, iron-3 was totally different. So actually, what you deliver with the suspended sediments or the icebergs is far more bioavailable, and therefore, no surprise, you actually induce chlorophyll changes very fast. So basically, you have 10% of the Earth's surface is now changed, because we have, at the moment, about 10% is covered by ice. But if you bring this back in the last glacier maximum, doesn't matter what this number is, it's about 30, or all the way to 100% to the snowball Earth, you can envisage that these changes in the aftermath of the deglaciation of these things had massive implication for the biogeochemical cycles. In my last couple of slides, I will actually show you why and what actually melts Greenland, because that's the reason why you came here. The problem is we cannot do a good prediction of why Greenland melts because we cannot really evaluate the albedo properly. Albedo, the amount of sun reflected from the ice sheet, is the biggest problem in surface mass balance models, and this is the prediction for 1 millimeter per year increase from Greenland, but actually it could be any of these. And in the IPCC predictions, we don't know. We would like to stay here, but we don't know where we're going because we have a problem with albedo. Why is that a problem? Well, in the last 30 years, obviously these are measured with satellites. And yes, people say, oh, MODIS satellite, its detector has been degrading, it doesn't quite work. But actually, this is a real difference between pre-2000 and after 2000 in satellite imaging average for albedo. Initially, this was only taking into account physical properties. Obviously, if you take a fluffy snow grain and you melt it, you actually change its property because you make it wet, and therefore you make it darker. That's the first change. And you have the general reflectivity of Greenland changes, for example, but you cannot explain this big change just by the physical properties. So if you go from dry to wet snow, for example, that explains a lot of the albedo, but not enough. The darkening, for example, of the Greenland ice sheet is not a simple and a single cause. I'm just picking this image. If you measure albedo here, 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 or here, you will get different numbers. You have to remember that satellite, MODIS, Landsat, or Sentinel, they will take pixel size of 250 or 500 square meters and actually average that. And obviously, at a large scale, it will work out. But it's not that simple, because obviously, if you look at the albedo here or here, it's a different thing. Why? Well, first thing, you have black carbon. Black carbon is soot. We're producing black carbon throughout the whole year through our anthropogenic industrial production. But we're also producing it through wildfires, and this is Fort McMurray, just, I think, a month ago. And all this black dust, which is soot, is actually transported to the atmosphere. Some of it gets transported to Greenland. Most of the time, wildfires are a summer event, but they actually reach Greenland. If you put something black on something white, duh, it will melt faster. The problem is, it is included in climate models, but it's based on measurements in spring snow. It's not, we don't yet know well what its chemical reactivity is. We don't yet know well what its fate in the summer is, how it reacts, for example, with the melting water. We don't yet know. So we have a rough idea what it does in the spring snow, but we don't yet know what it does to the increasing melt. The second part is the mineral dust. Obviously, you have dust storms, and they reach Greenland. Whether this is just from Sahara in this case, or from the proglacial environment, because you have more and more glacial retreating, and whatever they leave over is actually an Arctic desert. It's very dry because the water drains, and the minerals, the dust goes up and actually gets deposited back on the glacier. And only recently has this been considered in climate models. But again, we know very little about what, where, how much, and what it does. We have no clue what happens within the summer. We have no clue how the mineral dust versus the black carbon versus the changes in physical properties on the surface interact with each other. We have a guesstimate of between 0.1 and 0.5 reduction in albedo, but I might as well would have done that. The number is the same. And then, basically, if you look at this, dark is not just because of black carbon and dust. And I remember in 2004, when I went the first time with a bunch of people in the audience here to northern Svalbard, to Frederiksbrain, I saw something which really stunned me, because I saw red and green snow. And since then, I've been struggling in trying to understand whether this is important or just a fluke and something which I really like to do. But then more and more we looked at this, and actually, something like this really changes albedo. This is our red snow, sorry, that side, red snow and green snow. And you get, I'm not sure if you see it, really big blooms of this throughout the summer. And more, you see this. The same thing on the ice, and this has been discovered only a couple of years ago. You have colors which are brown, but you can have anything from yellow, green, brown, black, because it all depends on the pigmentation. And the same thing, the reason why these algae make their pigments is because when we go in the sun and getting too much, we put sunscreen on. They are smarter, they make their own sunscreen. But they make their sunscreen because they have to protect their chlorophyll from too much light. They are not considered important so far. They are not included in models. But compared to many of the other emissions, they are changing extremely fast in the summer. And with the lengthening melting rates, particularly from Greenland, they are changing dramatically. So what we did, we started in 2011, 2012. We went around the Arctic to about 21 locations. We sampled the bejesus out of these things, and we wanted to try to figure out what do the algae do. What we've seen is that you have all kinds of colors and all kinds of snow. Clean snow, green snow, red snow, clean ice, gray ice, and then you had cryoconi holes, which I'm not talking about, but many people have worked on these because they contain cyanobacterial communities, which also contribute a lot. But the important thing is that they all affect the albedo in very many different ways, because they're actually changing very fast over large areas. We have done both amplicon and metagenome sequencing, and this came out just last week, where we actually looked at the community composition. And what I'm showing you here is just the red algae part. Interestingly, they are cosmopolitan. It doesn't matter where you analyze them. They are all the same 6 cousins of the algae. Very, very low diversity. But interestingly, different to the bacteria, which we also analyzed, there is absolutely no correlation between the algae and any of the chemical, mineralogical, geochemical, biochemical, whatever parameters you want to measure. We measured 21 different ones. There is nothing. It's totally independent on location. The only thing they need, they're very, very non-needy. They just need liquid water. But what they do, considering that they are colored, is they affect albedo. And they affect albedo tremendously. A couple of numbers for clean snow. You go to green snow, you reduce it by about 0.4. Red snow, it's about 0.5, and gray snow, which is gray ice, which is the ice algae, it can go down to 0.35. So these numbers have made us believe that actually we have not just more melting, produce more algae, produce more melting. So you have this positive feedback mechanism, but if you just look at the red algae, they reduce albedo with all these measurements which you have by about 13%. Which is something which needs to be taken in consideration when you talk about climate models. So the bioalbedo component, which just come in this case from the algae, has to be included. The problem is we need to actually better ground through these numbers, not just over bigger areas, but also be doing all the different measurements together on the same plot. And that's where black and bloom comes in. Black carbon, bloom of algae, is a project which we start in about a week. The first people go up to Greenland in a week, where we basically combine, cross-correlate, and validate all kind of possible parameters on one single plot. So we will have basically a couple of MODIS pixels, so to speak, on the ice, which will measure everything under the sun. We're talking about 5 postdocs, 4 PhD students, about 9 PIs, having fun or not on the ice. We'll see. Important is that we measure in different places in Greenland. We measured both over time and over space. This is a UK-led grant, my last UK grant, led by the University of Bristol by Martin Tranter, but also together with people from University of Leeds, University of Sheffield, Aberystwyth, and obviously GFZ, myself, and Steffi. What do we do? Well, we'll combine measurements of microbiology, which we have now developed all the tools, we tested all the tools, we know how to do it best, because we now know how to quantify everything under the sun, but we have never done it as broad as we do now. We measure growth rate, we look at diversity function, we look at the relationship between light exposure, pigmentation, and nutrients on site. We combine that with particulates and microbes. That means we need to find out, if you take a sample from any of these sites, you don't just have algae. You have algae, you have black carbon, you have mineral dust, you have snow, you have ice, you have a lot of stuff. So we need to look at the black carbon components. We need to look at, this is dust, for example, in a snowpack, but we need to look at the minerals in the algae as well, and we need to look at all of this at the interfaces. Because only when we look at the particulates and the microbiology together can we potentially tease them apart. Because if you just measure the bulk, it doesn't work. And at the same time, in the same plots, we will measure quantify albedo, and we will look at broad bill albedo, because that's what we need to incorporate in the SMB models. And we do it both with static ones. This is Jason Box measuring, for example, algal bloom. But if you measure albedo here, here, or here, it will give you a different number. We'll do it sort of ground-based. We'll do it airborne-based, we have basically drones, but also look at the same time on the MODIS ones. And then, hopefully, we'll take all this together and quantify the influence of the biology, the mineralogy, the black carbon, the snow melt, all these parameters to link them, what we see from the ground, which we can now validate and ground truth with what we see from the air and from the satellites. And one of the postdocs will do the sensitivity analysis of these measurements, and hopefully we'll integrate all this in predictive models. So if you come back in 5 years, and maybe I'll give another talk sometime, I will hopefully show you some results. This is really exciting because it's one of the grants where besides the fact that it allows me to go back to my lovely place, which is the Arctic, it allows me to do a multidisciplinary work with people who are physicists, spectroscopists, modelers, remote sensors, microbiologists, mineralogists, and you name it. We have them all. I think we have even isotope people. Sorry, Friedhelm. So basically, I think we'll have a lot of fun with this, but basically I want to finish off with two things. We see that Greenland is melting. We see that there is an interaction between geology, biology, and mineralogy. I just found this yesterday. We had Schellnhuber et al. Schellnhuber is one of the guys who worked on the IPCC and is part of, very famous guy who did a lot of stuff about prediction. But he said something very nice. He said why the right climate target was agreed in Paris. We know that the target in Paris was just below 2 degrees. But he's just printed this. This came out last week, where he showed this is the West Antarctic ice sheet, and this is Greenland. If we stay in the Paris range, you can have a lot of different potential predictions. And if we stay in these two, we should be sort of okay. But one of the things he said, and I'm quoting, he says the Paris Agreement duly reflects the latest scientific understanding of systematic global warming risks, limiting the anthropogenic temperature anomaly to 1.5 to 2 degrees is possible, and obviously there is a but. It requires that we basically change what we do. Because if we don't do that, this may happen. And I'm sorry for those who are not from Europe, but I took the map from Europe. This may happen if all the ice melts. If all the 67 meters melt, we probably can write off Denmark, much of Northern Europe. London is probably bye-bye. Florence is gone, much of this part is gone, much of Russia is gone. We don't want to go there. And I'll finish up with my favorite cartoon. If you think of this, this is where we are now, at basically the ice age unit 0. If you think that if we go to 4.5 degrees increase, we're getting to +1 ice age unit, which would be here. This is in 86 years, we would have the picture from before. We don't even want to think about going to 2 IAUs, because this is 20,000 years ago, in the last glacial maximum, and if we would go to 4 IAUs, we would go back to snowball Earth. None of us wants this. And my last slide is this. Basically, we all live on a single planet. Regardless what happened in England last week, many people think that we are a bunch of different countries. We have different creeds, we have different nationalities, we have different knowledge of education or wealth. We're actually all one Earth, and as geochemists, we have the tools to take care of it in the future. Thank you very much. Everybody's happy, everybody wants to go to food.
Thanks again, Liane.
So please go to have your lunch, and please join us for the afternoon sessions. And think of this, you are not that part, we're all that part. Thank you very much.